Hi everybody, and welcome to your notes about Newton's laws. In this particular video, we're going to look at Newton's first law, and then I'll have another video about Newton's second law. You have both of these notes together in your OneNote notebook, so just watch both videos and then fill in the notes as we go. Be sure you draw all your diagrams. So we're going to talk about free body diagrams. There's going to be lots of arrows we're drawing. Be sure that you add those into your notes. Okay, so before we start talking about Newton's laws, let's go over a few facts about force. So we're going to measure force. The standard SI unit for measuring force is going to be the Newton. This is not on your slide, but you need to add this on. A Newton is equal to 1 kilogram times a meter divided by a second squared. Okay, so a Newton is a kilogram meter per second squared. Now we can define force as being either a push or a pull, and it can exist during physical contact, or it can exist when there is no physical contact. So if I have two objects that are rubbing against each other, so there's going to be a frictional force between those two. If I'm pushing on something, I'm applying a force to it. Those things require physical contact. But if I were to drop a pencil and it falls, the earth is pulling down on that object, but the earth's not actually touching the object, right? So the earth and the pen that's falling are not in physical contact, but the pen is inside the earth's gravitational field. So if we have forces that can exist across space without contact, we call those field forces. Gravitational force is an example, the electric force is an example, and the magnetic force is an example of that. Okay, so Newton's first law is also called the law of inertia. So before we talk about what the first law is, we need to define what inertia is. So inertia is a quantity of matter that we measure whenever we're measuring mass. Okay, so the unit for mass is the kilogram. That's how we're going to measure an object's inertia. So the more mass an object has, the more inertia it has. And inertia is an Italian word for laziness. Now, inertia is different than weight. And so mass is also different than weight. Weight is a force due to gravity. Okay, and it's how much your mass is being affected by gravity. And those two may seem like the same thing, right? Something that has more mass is going to be heavier than something that doesn't. Except for one small problem. That's assuming that we're in the same gravitational field. Well, let's look at mass and weight in different gravitational fields. So I have this question here that says, what is the weight of an 85.3 kilogram person on Earth? What about on Mars? On Mars, the acceleration due to gravity is 3.2 meters per second squared. So this is the measurement of the person's inertia, or how much laziness it is, how hard it is to get that thing moving. Okay. Now the weight, though, is the force due to gravity. So to figure out weight, we're going to take the mass and we're going to multiply it by the acceleration due to gravity. This is an important formula for you to remember. Weight is mg. So on Earth, the mass of the person is 85.3 kilograms. The acceleration due to gravity is 9.8 meters per second squared. Remember, a kilogram times a meter divided by a second squared gives me a Newton. And on Earth, this person has a weight of 835.94 newtons. Now on Mars, the person has the same amount of mass, right? 85.3 kilograms. The person didn't get larger or smaller when they went to Mars, right? But the acceleration due to gravity is much less, so they end up with a much smaller weight. Okay, so mass and weight are different. Mass is a measurement of the inertia of an object or its resistance to change, and weight is a measure of the gravitational force on the object. Now let's look at Newton's first law. So this is the law of inertia. An object in motion remains in motion in a straight line and at a constant speed, or an object at rest remains at rest unless acted upon by an external unbalanced force. So there's two conditions here and one constraint. So the two conditions where this law applies, condition number one is that the object can move, but it must be moving at a constant speed. If the object's moving at a constant speed, Newton's first law applies. The second condition, the object could also be at rest. Okay, so if the object's at rest, Newton's first law applies. Now the constraint to this is as long as the forces are balanced, and if all the forces are balanced, the sum of the forces is zero. So it's not that there's no force acting on the object, but that all the forces that are acting on the object have to be balanced. If it's balanced, then it's in one of these conditions. It's either moving at constant speed or the object's at rest. So the bottom line here, right, for these two conditions is that there's no acceleration, right? So if there's no acceleration, all the forces cancel out. We say the object is in equilibrium. And so here's a little mathematical formula for that, right? If the acceleration is zero, I'm either moving at constant speed or I'm at rest. Then the sum of the forces equals zero. This is a Greek letter that just means sum together. You're going to add together all the forces, and those all equal zero. So one thing when we're looking at forces, we need to be able to draw free body diagrams. So a free body diagram is a pictorial representation of forces complete with labels. So these are some real common forces that you're going to see. Weight is mg. We just saw that, right? The mass times the acceleration due to gravity. I can also have this thing called the normal force. The normal force is a surface force always drawn perpendicular to the surface. If I have an object resting on a surface, that surface is holding it up, right? So there's a force coming from the surface, and that's always perpendicular to the surface. A tensional force exists in a rope or a wire or a string, and it's always drawn away from the object. If you think about it, I can pull something with a rope, but I can't push it with a rope. I can't push inward to the object with a rope. I can only pull it away. And then frictional force is whenever something is moving or trying to move along a surface, right? And so it's rubbing against something, and frictional forces are always going to oppose the direction of motion. So let's take a look at the situation here. I have one object sitting on a table. That object's tied to a rope that goes over a pulley. And then I have another object down here that's hanging, right? So if you think about what's going to happen here, if I let this thing go, gravity is going to want to pull this down, right? And then with gravity pulling this object down, there's going to be tension in the rope trying to pull this object to the right. Well, let's go through and label all the forces. First of all, we always have the force due to gravity, right? If we're in a gravitational field, which we are on Earth, we're always going to have the force due to gravity. So I have two objects here. There's two forces of gravity, one on each object. The first one I could call W1 for weight 1. Or I could call it Fg1, the force of gravity 1. Or I could call it M1g, mass 1 times the acceleration due to gravity. Over here, I'd just call this M2g, or we could call it W2 or Fg2. But this is just the second force of gravity. So this is the weight of this object. This is the weight of this object. Now, this one's sitting on a table, right? So if gravity's pulling it down, something needs to be holding it up. That's what the normal force is. So the normal force always acts perpendicular to the surface. The surface is horizontal, so the normal force is going to be pushing upward. Then I have a force here, and I have a force here. And that's going to be the tension in the string, right? If you think about it, gravity's pulling this down. Well, what's resisting it? What's holding this object up? Well, that's the tension in the string. Over here on this side, this tension is pulling it to the right, right? The tension is what's going to cause us to want to slide to the right. Now, these tensional forces are actually equal. They're the same because it's one single rope, right? So if I have one single rope, and if we can neglect the mass of the rope, then the tension inside the rope is equal on both objects. Now, this thing is also sliding along a table, so I have the force of friction as well, assuming that friction is a reasonable amount on this table. Okay, let's look at this. Now I have an object sitting on an incline. Now I want to draw the free body diagram for it. Remember, it's just a pictorial representation of all the forces acting on the object. First thing we always have weight, right? So mg pulling down on this thing. I don't need m1g or m2g because I only have one object. So I'm just going to call it mg. It's the mass times the acceleration due to gravity. Now, it's also sitting on a surface, right? But the surface is in an incline, and the normal force to an object has to be perpendicular to the incline. So the normal force doesn't just go up. The normal force is perpendicular. So that's why this little square is here to show there's a 90-degree angle right here, and the normal force is pushing up from the surface. And then lastly, I also have frictional force, right? This thing's going to want to slide down the ramp, so there's going to be friction opposing the motion. Friction is always going to be parallel to the surface, right? Opposite the direction of motion. Okay, so Newton's first law in equilibrium. Since the net force on the object, since when you add together all the forces, they're going to equal 0, a system must be at constant speed or at rest. And so we call that equilibrium. Some tips for some of these problems. Always draw a free body diagram. Any forces that you have that are at angles, you're going to want to resolve those into x and y component. Then write the equations of equilibrium. So the equation of equilibrium just says the sum of all the forces in the x direction needs to equal 0. The sum of all the forces in the y direction equals 0. And then you're going to solve for your unknowns. So let's take a look at an example here. Right? I have a 10 kilogram box being pulled across the table to the right at a constant speed with a force of 50 newtons. So that term constant speed tells me that all my forces need to balance. And then it's asked me to calculate the force of friction and then also calculate the normal force. So my first step for this is going to be to draw a free body diagram. I always start with mg, right? There's always the force of gravity pulling down on this thing. Now it's sitting on a surface, so I also have the normal force holding it up. I'm pulling it to the right with a force of 50 newtons. I'm going to call that Fa. That's going to be my applied force, right? We're applying a force of 50 newtons. And then I've got the force of friction because it's sliding along a surface. I've got the force of friction going the other way, opposite of the motion. Okay, so let's take a look in the x direction, right? So in the x direction, I have Fa going to the right, and I have the force of friction going to the left. Well, those two things need to add up to 0, which means they have to be equal to each other. So Fa, the applied force, equals the force of friction, and I was told the applied force was 50 newtons. So that answers question A, right? The force of friction also has to be 50 newtons. Those forces have to be equal in order to be at constant speed. Now let's take a look in the y direction. Right now I need to calculate the normal force. Well, the only up force I have is the normal. The only down force I have is mg. And those two things need to be equal to each other. They need to cancel out. They need to be balanced. Again, because I'm moving at a constant speed. So mg equals Fn. Well, I was told the box is a 10 kilogram box. That's my mass. Times g of 9.8 meters per second squared. That gives me 98 newtons. So in this case, mg and the normal force are equal to each other. Now let's say I have the same box, but now I'm pulling at an angle of 30 degrees above the horizontal. So I'm not pulling to the right anymore, but now I'm pulling up at an angle. So my first force I'm always going to label is going to be mg. It's sitting on a surface again, right? So perpendicular to the surface, I have the normal force. But now I've got this force at an angle. This is my applied force, right? And that's going to be acting at a 30-degree angle. And then I also have the force of friction pulling back the other way. Now this is the same situation as before, where the box is moving at a constant speed, so my forces need to balance. Well, let's look at the force there. There's my force of friction label, right? Let's look at that applied force. That applied force is made up of a component that is in the x direction and a component that's in the y direction, right? Because it's at an angle, there's some force acting horizontally and there's some force acting vertically. So once I have my diagram and I have my forces and my components, I'm just going to look at what do I have in the x direction. Well, pulling to the right, I have the x component of the applied force. Well, this is the adjacent side of the triangle. It's just going to be the applied force times cosine theta. So that x component of the applied force is going to be 50 cosine 30, which is 43.3 newtons. Well, that's the only force to the right I have. So that force to the right has to balance with the force to the left. So I know then that the frictional force is also going to be 43.3 newtons. Now let's look at the vertical direction. In this case, the normal force does not equal mg, right? I have the normal force going up, I have mg down, but I also have this y component of the applied force going up. So my up forces need to be equal to my down forces. Rearrange that a little bit, and then the normal force is equal to mg minus that y component. Mg is 10 times 9.8. minus the y component, which is 50 sine 30. And I end up with 73 newtons. Notice the normal force is less in this example than it was in the one before. Well, what if the object is not in equilibrium? So what if it is accelerating, right? Newton's first law only applies at constant speed or at rest. That's where the forces cancel and I have no acceleration. Well, if it is accelerating, if I do have these unbalanced forces, that's when we're going to need Newton's second law. So we'll talk about that in the next video.